So, let us see how we can get it into the a form that we can solve, right. So, let us just rewrite our equation over here. I had del squared E minus E I, that was my first term. I had my k naught squared epsilon r of E minus k naught squared E I. Okay. Now, the hint was that I want to get E minus E I as the common variable, both for del squared and k naught squared term. That is the first constraint. Second constraint was what? Right. So, the second constraint was in this equation 4, this guy was what? Was it constant or a function of space? Constant. So, these are the two things I have to sort of fit in so that I can use Green's function. So, what can I do over here? I want to remove this guy from the left hand side because it has a function of space. Epsilon r is a function of space. So, what can I do? Just move it to the right hand side. I can do something like that. But if I move it to the right hand side, I no longer have a E term to go along with k naught squared. So, very simply what I can do is, let me add and subtract a common term. So, what if I add k naught squared E on both sides? So, then this will become del squared E of r minus E I of r. First term is fine. I can gather the k naught squared together. So, what will happen? I have E r minus E I r, right. So, I have got what I wanted. Now, whatever is unwanted, I should move to the other side, right. So, the other side will be what? So, the other side, this term will continue to be there and this guy moves to the right hand side. So, I have a minus k naught squared epsilon r minus 1 E of r, right. So, now this looks like a form that we can solve using our Green's function. Why? Simply because the operator is common, del squared plus k naught squared has appeared on both sides. Okay. So, when we had, okay, just wanted to rewrite one thing over here. When I had these two equations, how did I write the solution? Phi of r was written as, combining these two equations, I can write phi in terms of f and g as the convolution, right, and that convolution was minus. So, g of r prime f of r prime dr prime. Okay. So, now we can make use of that for solving this equation, right. So, using del squared g of r prime plus k naught squared g of r prime, we get, so the variable has to be held the same. So, it is E r minus E I, right, that is what is going to be equal to the convolution now of Green's function.
So, we do know what E I is.
We know what E I is, and the entire right hand side over here, one of those minus signs got cancelled. Right. Is that fine? Okay. Does this, and what is the so the region of integration is going to be the full volume V1 plus V2. Okay, that makes it most general. Where so this is the expression that we get. Now, looking at this expression, does it have all the information about the problem inside it? So, let us write down what is known. What is known in this problem? I know the incident field. What else do I know? object shape permittivity I know, which is all encoded into the relative permittivity, right. I also know Green's function, and now I can use the closed form Green's expression which I had derived previously. Why? Because I am using this equation and I know the solution to this equation. And what is unknown? Right, the electric field. This is what is unknown. Now, looking at this, what kind of a, first of all, is it an integral equation? Yes or no? It is an integral equation. Why? Because the variable of interest, which is the unknown variable, is it appearing inside the integral sign? Yes, here it is. But which kind? We have studied different kinds of integral equations. What kind of differential equation, integral equation is this? Fredholm integral equation of the second kind, because the unknown is both inside and outside the integral sign, right. So, we will just make a note of this. This is a Fredholm integral equation of second kind. Okay. This is what the math people call this equation. If you study quantum mechanics and calculate scattering cross sections in quantum mechanics, you get actually the exact same equation, and the physics people call it by the name Lippmann-Schwinger equation. So, if you read a physics book, you are likely to hear this word for it. If you read a more W or math book, you will find Fredholm integral equation of second kind, but they both refer to the same object. Okay. So, let us now sort of massage this equation into a form that we can solve. Okay. So, what you would do is standard technique, gather all the unknowns on one side, move as many knowns as possible to the right hand side, right. So, turns out to be a very simple thing to do. I just have to move the integral over here. Now, it is sort of convenient. Can I make the region of integration smaller than what I have shown right now? Right, this was our V2, this is our V1. So, I am integrating over V1 plus V2, that is what I said, the most general case. Can I make it just V2? Look at the integrand, is the integrand non-zero everywhere? Look at this term, right. This term is non-zero where? Only inside V2. Outside V2 in the region V1, it is vacuum. So, what is relative permittivity of vacuum? 1. So, this term, this integral over here, our life has become simple because automatically it is restricted only to the region of interest V2. Okay. So, it's yes, this is R prime, correct. Now, what am I finally interested in? I want to know the field somewhere outside here, right. That is where I want to find out the field. For example, this V2 could represent an aircraft and I want to calculate its radar cross section, or it could be some new Wi-Fi antenna I have designed. I want to see how it is the radiation pattern of this, right. So, I want to find the field everywhere. So, if I plug in a value of R belonging to V1, what is the problem with this equation? So, supposing I put R is equal to some point inside V1 here. So, I will get an expression for ER is equal to EI plus this term over here. In this term over here, I do not know one quantity, which is I do not know the electric field inside V2. So, I can't actually use this equation right now. So, what is the first step I should do? If I know the field inside V2, if I know E inside V2, am I done? Yes. If I know E inside V2, then the integral I know, I know, therefore I know E everywhere. So, we have already come across this trick earlier. Integral equations are always solved in 2 steps. So, the 2 steps are, in this case, the first step is find E of R inside V2. This was like our the electrostatic example we had of the charge on the rod. First find the charge, then find the potential everywhere. You can't directly find the potential everywhere. So, first find E inside V2 and then find ER anywhere. Okay. So, for step 1 I have to somehow get into formulating a system of equations, and we have seen the framework for it, and that framework is integral equations. What is the framework for solving integral equations we are talking about in this module? Method of moments. So, method of moments is what we will use to solve this integral equation. Okay. So, we will use the simplest method of moments that we know so far, which is pulse basis delta testing. That is what we are going to do. Except that now I have a 2-dimensional volume in which I have to find out pulse basis functions. In the surface integral formulation, I had a line and I had pulse functions on that line. So, now we are sort of becoming a little bit more general. Okay. Yeah. Okay, so let's look at it a little bit systematically. In the first step, I will choose R belonging to V2. Okay, for in this equation, I will substitute R belonging to V2, various points, and solve it, which we will discuss how to solve. At the end of it, I know ER completely inside V2. Now, when I come to here and I choose R belonging to V1, then you see the domain of integration remains V2 over here. So, I still need ER inside V2, even though I am putting R belonging to V1. R belonging to V1 goes in over here and in this R, everything else remains the same. That is going to be 0 outside V2, because see the variable of integration is
integrating over V2, right?
Yeah, only over V2.
So it's not going to be
Inside V2 this term does not go to 0, you are right. That is why we have made the region of integration only V2. Okay. So, that is our
so it was initially V1 plus V2.
it was originally the region of integration was V1 plus V2, then we realized we do not need to also include V1, because that integrand is itself going to 0 outside V2, right. So, we made it a little bit simpler. Now, coming back to our how we will actually solve this using the method of moments. So, pulse basis and delta testing. Okay. So, here is my object. Okay. Now, I am just going to show you V2, and now as we have discussed, we are discretizing the volume. So, if I am discretizing the volume, I need to sort of make a grid like this. Okay. The grid is not going to be exactly capturing the object. Okay. So, this is just a cartoon representation. As I make the size of the pixels, now these are called pixels, as I make the size of the pixels smaller and smaller, better is the approximation of the surface. Okay. Later on you can go become fancy and choose non-rectangular units, you can make triangles, you can make whatever you want. Okay. But the basic idea, let us try to understand. So, having shown you the grid over here, pulse basis means whatever is the variable of interest is expressed in the pulse basis function. So, what is the variable? Electric field inside V2, right. So, I will write E R So, what have I said? I have divided this domain into capital N pixels, and this pulse basis function is 1 in the nth pulse and 0 everywhere else, right. So, if I take for example if I take this to be the nth pulse, so this I am being a little lazy in just writing R, actually it is the vector R, right. It is a 2-dimensional problem, so it is a vector R. So, this Pn of R is 1 over here and 0 everywhere else, right. So, it is like it is a column of height 1, 0 everywhere else. These are my 2D pulse basis functions. So, remember that these are 2D pulses. So, the unknown was electric field, now the new unknown is ANs, right. So, I have to solve for these, okay. Now, if you look back at this equation over here, this is what I am discretizing as pulses. There is this term also over here which is going to appear everywhere. So, may as well discretize that also into pulses. Okay. It will become, because when I do the integration will split over all the pulses, right. So, I am going to write this epsilon r minus 1. By the way, this it gets irritating to write this epsilon r minus 1 every time. So, there is a new variable that you use for it, you just call it chi of r. Okay. Yeah, pardon me? It's yeah, this is not susceptibility. Well, yeah, this is, you can call it susceptibility. Yeah, okay. Which is going to be also written in n is equal to 1 to n, right. So, I will call it x n p n of r. Okay. So, this is just a discrete representation of permittivity. Just remember that x n is known, it is not unknown. Okay. It is given to me in the problem, the permittivity of the object is given to me. Okay. So, let us, it will amount to one and the same thing. Okay. But the fact is, you know x n, so there is no point in combining x n and a n into one, because you know part of it and you do not know another part. So, we will just keep it separate. So, let us just look at our equation once again. So, I had E of r minus k naught squared g of r prime chi of r prime E of r prime dr prime is equal to E I of r. That was our equation. Okay. So, now the first step is to put the pulses in, right. So, this first term will become summation a n p n of r. Okay. Second term is over V 2 over V 2 k naught squared, g remains as is, okay, and then comes the summation. So, I can write this as x n a n p n of r dr prime is equal to, I have just substituted, right, product of two pulses is still a pulse, fine so far. So, we have taken care of the first part. The next part is delta testing. So, when I say testing, what do I am taking delta functions for the testing. So, what am I doing? I am taking the inner product of both sides with the testing function. The testing function is, in this case, delta of r minus r m, let us say, where m, let us say, is the center of one of these pulses. So, we can call this as r m. So, in testing, what will I do? I will take this left hand side and multiply it by delta of r minus r m and integrate over dr. So, the question is this E r over here, is it E r or E r prime? Is that your question? It is going to be E r.
But that is, now you are measuring V 2, right?
This is being integrated in V 2, yes, but it is outside the integral sign, right. When we derived this, let us go back over here. We started with this equation and used the Green's function to solve it. So, when I took the difference and integrated over here, r is constant for this integral. So, this is r and this is r. Okay. So, that is why this is continues to be r and not r prime. Inside the integration, this is r prime. Getting back to the testing function, I have to apply this testing to both the left hand side and the right hand side, right. So, this whole expression I can put inside over here. That is the meaning of doing testing. So, what will that become? So, take the delta function, delta of r minus r m. This is my testing function, the mth testing function. Okay. So, I am taking one testing function which is an impulse located at r m. First term over here, what happens to the first term?
This delta function is also 2D.
It is a 2D delta function. What happens to the first term? Let us go step by step. I have a summation over n pulses. Which pulse survives? The mth pulse will survive. What is the magnitude? AM, right? The summation goes away, I am left with AM because the delta function annihilates all but one pulse. Going in further, this is where we have to do it a little bit carefully. What will happen over here? So, will the summation remain or will it go away? So, the question is, for which coordinates is this delta function defined, primed or unprimed? Unprimed coordinates. Inside the integral, which is the quantity which is a function of unprimed? The summation and all are all over primed coordinates. So, what is the unprimed quantity here? Only g. So, what will happen to this integral? The integral will remain because it is an integral over primed coordinates. The function which is of unprimed coordinates is only one g. So, what will happen to that g? GRM, exactly. And the integral and the summation, will they go away? No. So, I will get V2 k naught squared GRM r prime summation n is equal to 1 to n xn an pn r prime dr prime. What happens to the right hand side? It is also involved in the testing. EI of Rm. Excellent. So, this is what pulse basis and delta testing has done to our equation. Can I solve this equation? It looks a little complicated, but in principle it is clear. There are knowns and there are unknowns. I can solve this equation over here. Okay. So, let us see, there are sort of two possibilities over here. Remember that G over here has it's a Green's function. It blows up at r prime equal to Rm, right. So, that is something that we have to be careful about. But before we get into those details, let us be conceptually very clear what is happening. So, I will just take a 3 by 3 case. Okay. So, let us call this to be, this is my Rm. Okay. So, what is this integral doing? This is an integral over entire V2, right. This whole thing is my V2. And what am I doing? I am running over this entire region, keeping Rm constant. So, for example, R prime first let us say belongs to this, let us say this is the nth pulse. So, then g of r prime, what was this function? This was h naught, so it was minus j by 4 h naught 2 k of r, or k naught of r minus r, right. That was the definition of Green's function. Take the 2 points and take the distance between them, that is what it was. So, then what remains? So, when I am doing this integration, I am Rm is being held constant, this distance is what is varying over where? Over this nth pulse, correct. So, I am holding Rm constant and integrating over this, then this, then this, over all of these pulses one by one. That is the meaning of the left hand side, the second term over here. When I integrate over this pulse, what is the coefficient involved? Unknown coefficient involved is? So, if this is pulse 1, 2, 3, 4, 5, 6, 7, 8, 9. So, when I do the integral over here, which of the A's will appear? A1, right. When I come here, A2, A3, A4 all the way up to A9. So, this term over here that I have written is, since it is a summation, I am going to get A1 something plus A2 something all the way up to A9 something, right. And which term will come over here? Here Rm is chosen to be R1. So, this will just be A1. So, I will have one equation, how many variables? 9 variables. A1 to A9 are my variables. I have got one equation, 9 variables. So, the procedure would be repeat for all 9, I get a 9 by 9 equation to solve for. Okay. So, that is the strategy that we will follow. Okay. Is it clear what is happening over here? Okay.